All right, kiddos, you should have had enough time to at least know whether or not you knew what you were doing. Let's go ahead and collaborate in your groups. Make sure everyone's solid on how to do long division. And maybe some people have even finished it already.
Because I got to do
Okay. So you distribute the negative and then you give bottom. And you would get negative 5x squared, so you have to bring down 0x. And then you distribute them. And then your remainder is 0. I mean, like yesterday she did synthetic division.
All right.
I don't think I
Finish up explanations in the next 15 seconds. Okay, you guys kind of got it?
Yeah.
Perfect. Grace, what's the first thing we should try? What would you?
Find the x cubed, and so you find what times x makes x cubed.
Can you get?
X squared.
Perfect. So let's keep going. Caitlin, so what do you do next?
You distribute the x squared.
And you get?
X plus 5, and you get x cubed plus 5x squared.
Trevor, what next?
We distribute the negative.
Good. So subtracting the whole thing. And what happens when you distribute that negative? Good. Jaden, what next?
And then I put negative 5x.
Good. Probably looking at that and that, right? Cool. And what do we do with that negative 5x?
I distribute this to the plus 5.
Okay. And what'd you get?
Negative 25x.
True. Along with,
Oh, and then I drop the 0 down as well.
and then what happens when you multiply negative 5x by x?
It's negative 5x squared.
Blair, what next?
Subtract.
Good. And technically I would throw in the same word as Trevor with distribute. Good. And what do you get when you distribute?
5x squared.
Good. Sorry, it crossed out and I wasn't even paying attention. Yeah, good. They cancel out and then 25x. Chris, what next?
I don't know.
Okay, well, we have this
Bring it
guy.
down.
Let's bring him down. Good. And then what people have been doing is taking this guy and seeing how many times in the beginning part of every. This guy, how many times? This guy, how many times? What would you need to multiply by x to get? So if we put a plus 25, and then hopefully you've been hearing a lot of people saying distribute. Distribute, distribute. So if you multiply the 25 by x, what do you get?
25x.
Distribute the 25 times 5. Then going back to what Blair just said and then Trevor said before.
Distribute the negative.
Well, subtract and then distribute the negative. And in this one, doesn't always happen, but in this one, everything cancels. So what's our remainder?
0.
Which means, do I have to put anything else additional up here in the answer?
No.
Question, everybody. Did they match?
Yes.
Now, synthetic is a shortcut. Some of you saw it last year in Algebra 2. Some of you, if you came from a different school or a different place, maybe not. Synthetic is a shortcut. However, do you remember yesterday? Can we always do a shortcut?
No.
Remember what I said for this problem that made it so synthetic couldn't work, wouldn't work?
Because it has to be
when you're dividing by an x that's not to the first power, we can't use synthetic. So I showed you long division first because it always works if you need to divide one polynomial by another. But when you have a problem, what were you dividing by this time?
X plus
X plus 5, which has x to the first. When you're dividing by any factor of the form x minus a, you can use synthetic, which, I mean, guys, look at this. Doesn't synthetic look way easier? Hopeful. But once again, long division does work. Synthetic is a shortcut. We need to talk about it. And we like shortcuts, but some of you need the words to talk about. So I'm not apologizing for the words, but I am explaining why I have the words. Just a few of you, the words help. Because they kind of work out. The words help because they work out what we just did. Sorry, for some reason it's missing my... There we go. Okay, so you saw me do an example once. We're going to do an example again. We have some further applications of division to talk about today. Some of them will be kind of cool. Some of them will be shortcuts. All of them are helping us learn how to factor big old polynomials. I'm going to kind of put a few things in the box in just a second, but let me go ahead and just let you guys write. You can even write down the example if you want, but we're going to solve it on the next page. And as you guys are writing, these two are very similar and a little different. I'm going to give them different names. X equals a, we're going to call it 0. X minus a, we're going to call it factor. X equals a, we're going to call it 0. X minus a, we're going to call it factor. As you guys notice, as you wrote, the very first thing you wrote, hopefully, synthetic, yes, is a shortcut, but remember when I was telling you it only sometimes works? It works if we can write the factor in the form x minus a. If we can write it in that form, that's when we can use our shortcut. Remember, when we do this shortcut, the book, I think, shows something like this. I don't know, I don't like it, it's kind of messy. I like instead what is more traditionally shown with synthetic, where you have a little box signifying the division. A is what goes in the box. The 0 goes in the box. Not the factor, not the negative a, but just the a, the 0. And then you have coefficients. I'm not going to actually make them. I could do like b, c, d, but that's kind of confusing. Just coefficients for the x cubed term, the x squared term, the x term, I don't know, the constant term. You're going to have a different number based on what the degree is. You always bring down the first number. So you put your polynomials coefficients here, which you're dividing into. Put your a here from what you're dividing by. That's step number 2. Number 3, carry down the first coefficient. Just come straight down. And then the pattern is you multiply, put it here, and then you add down. So you multiply what's in the box by what's down below, carry it up, and then you add down. Then you're going to do the same pattern again with the next one. Multiply, carry it up, keep on coming, then add down. Multiply, carry it up, then add down until you have the last one. And the last one will always be your remainder. The last one will always be the remainder. And the answer will always be 1 degree less or lower than whatever you started with. Now we did an example. I'll do another illustration. Yesterday I did it super fast. And for those of you that remembered synthetic, it was enough to hopefully be like, oh, I can do this, and maybe you researched it a little bit to be able to work on homework last night. But for the rest of you, it wasn't like a full, let's review the whole process. So we have our words. Let's go ahead and same example that you just wrote. I'm just giving myself space. Same example you just wrote. I'm just giving you space. Kiddos, what's going to go in the box?
First one saying before we run plus.
It very well could have been, because I make mistakes like that all the time. But thanks for checking. I appreciate it. So x minus 3 is the factor. So positive 3 is what goes in the box. Good. It's the 0 of that factor. What coefficients go out to the side?
6, 7, 1, 26.
We don't have to do any zeros because we have every single possible term. The cube, the square, the single, and the constant. The steps in the page before, after putting the coefficients, after putting the 0 in the box, we carry the 6 down, right? Now what? Good. Multiply what's down by the number of the box, so 18. Carry it up and add down. 3 times 25, 3/4, how many cents? Add down. 3 times 74, hey. Some of you can do this in your head, some of you need to write it out, and that's okay too. Then add down, 6 and 2 is 8, 2 and 2 is 4, 0 and 2 is 2. What's this last number symbolize? So my question to you is, does x minus 3 go evenly into our polynomial? The answer is no. But what does this show us? This shows us it doesn't go in evenly. That's good. It shows us a couple things. It shows us if we take 6x cubed plus 7x squared minus x plus 26 divided by, if we simplify that fraction, we do end up with, well, hold on. How would we write this answer? 6 and 25 and 74? Good. We had an x cubed. If we take away a linear from an x cubed, we're going to have a quadratic left. It's a positive 25. It's a positive 74. So whatever this term was, this was our x cubed term. The answer, the quotient, is always going to have 1 degree less. Counting down. So it used to be a cubed, squared, single, constant. Now it's a squared, single, constant remainder. So what this tells us is, divide the 2 and we end up with a quadratic. Divide a cubic by a linear and you end up with a quadratic. Does it make sense why I'm writing 248 over x minus 3?
All because when we have that, then we get to divide
Yeah,
by
like a long division. We take this and we put it over who we were dividing by. So that's technically true. That's one statement we can make. But today we're going to see it's also going to be helpful to think about this another way, which is really just rewriting the statement. From this division, we can also say 6x cubed plus 7x squared minus x plus 26 is equal to x minus 3 times 6x squared plus 25x plus 74 plus 248 over x minus 3. We can also say that this shows the division and the answer from the division. This shows the possible factorization. But it's not a good factorization unless it's even. What do I mean by that? Unless there's no remainder. Because right now this is a mess. To have x minus 3, this guy, I just moved him to the other side. I can see not only the division and make that statement, I can also say, hey, guess what? This polynomial is this guy times u. If we're trying to factor, do we like the second factor to have fractions in it? Fractions with x's in it? No. So as we said earlier, x minus 3 does not go evenly into this polynomial. It doesn't go evenly into the polynomial, but we technically still can say this polynomial is x minus 3 times somebody. It's just not a good factorization. Now there is one last statement we can say. I want you guys to go ahead and plug in In your calculator, grab your calculator out. It's okay. Unless you're really good at mental math and you can take your time and do mental math. Can you plug 3 into the original function, meaning into this guy? Into 6x cubed plus 7x squared minus x plus 26. You can use the cool plug the function in your y1 and do your alpha trace y1 of 3. You can use that from the graphing calculator handbook. Or you can just, from the home screen, do 6 times 3 cubed plus 7 times 3 squared minus 3 plus 26. Go ahead and plug it in. Let's see who he is. What? Where do you see that in this work? The remainder is the exact same thing as the function value. Is that always going to be true? In this one, would it have been easier for most of you, mental math, no calculator, to do 6 times 3 cubed plus 7 times 3 squared minus 3 plus 26, or to do the synthetic? I think a lot of you would say it would probably be easier, that you would make fewer mistakes if you did the synthetic. Some of you are like, no, I can plug in better. Okay, that's good. But for a few of you, maybe synthetic might be a shortcut to plugging in. Who would have thought that? Maybe synthetic is actually a shortcut to plugging in. Interesting. Let's keep going though. There's actually a theorem for this. I don't even think I give you the actual name of it. It's called the factor theorem. I think it comes up in your homework, and when it does, the directions are super clear about what to do, I think. So if you want, you can technically talk about or reference the factor theorem. Long story short, we can use synthetic for not only dividing, but we can also use it for talking about factors and function values, and that's what's going on here. We can use synthetic to talk about factors. Spacing gets all funny. We can use synthetic division to talk about function values and about factors. Sometimes it's easier to do synthetic to get function values, and sometimes it's easier to do function values to check what's going to happen in the synthetic. So long story short, you can check the remainder that it's right by plugging in x equals a to the original function. You can check the remainder by plugging in, or you can check the plugging in by doing synthetic and having a remainder. They can check each other. And then the example on the page before, I asked you, does it go in evenly? And you guys said no. Almost all of you got that, I think. I asked if it went in evenly. You said no, and the reason being, once again, there's a remainder, yeah. It doesn't go in evenly. So what would need to happen for x minus 3 to go in perfectly evenly? What would have needed to happen? Yeah, the remainder would have been 0, like this guy. Did this guy go in evenly? Yes. How did we know? Remainder was 0. So, if something goes in evenly, if the function value is 0, or similarly, if the remainder is 0, if the function value, we've just learned, well, that's the same thing as the remainder. So if the function value is 0, if the remainder is 0, then I know that x minus a is a perfect factor. It is a factor that goes in evenly. This is similar to something like, Calc BC killed my boards. Didn't we use 47 over 6, or 47 over 16, something like that? When I was introducing long division, I think that was it. Does 16 go into 47?
Yes.
Yeah, it does. Not even. 16 goes in, and we did that the other day, didn't we? We had 47, we had 16, we guessed it was 2, and that's going to be 32, right? And we have 15 left over. It goes in 2 and 15/16 times. Ugh. Does it go in evenly? No. Does anything go evenly in 47? 1 in 47. So the difference between going in and going in evenly, we can divide polynomials. We can divide one by another, and it goes in some way. But if we're looking for factors, we're specifically looking for it going in evenly. This one down below, I think I have a page for it. Let's go ahead and go to the next page. This is the example right down below. Pretty sure I wrote it correctly. Okay. Question. If remainders can check function values and vice versa, which one looks easier to start with on this one? Plugging in or remainder? Yeah. Why? Because you're just plugging in a 1. Now, a second ago, what would we, or what did we have to plug in? A 3. Maybe synthetic was easier. But in this one, I'm pretty sure plugging in is easier also. So let's plug in, and then we'll see if the synthetic still works and if the remainder still works for checking the function value. So, plugging in 1. Remember, 1 goes in the input spots, which is marked by the x. X marks the spot where 1 has to go. We end up with, PEMDAS says, do the 1 cubed first. Do the 7 times 1 second. I know, I'm showing all the work. 5 minus 7 is negative 2. Do you guys agree? So even though they said to use synthetic to check, well, let's plug in. Let's figure out what we think it is. Then let's do synthetic. So who goes in the box? Careful. Negative 2 is hopefully what ends up way over here in the remainder spot. 1. Why? Does that make sense? Back here, we plugged in 3. Oh, sorry, wrong one. Back here, we plugged in 3 because 3 was the 0 of the factor that we were trying to divide by. So we're plugging in 1, a equals 1. The coefficients, well, hopefully you guys see, that comes straight out of the polynomial. 2 and then 0. Then negative 7, then 3. And that's what these are. Okay, you guys get the shortcut? Who comes down? Multiply. Add. Multiply. Add. Multiply. If you ever have a time where the remainder is different than the function value or the function value is different than the remainder, you've made a mistake. Which could be nice for a test. If I say to do this, you can double check it with another way. An entirely different way. Or vice versa, you can check with plugging in. Depending on where your strength is. Maybe you're stronger at plugging in, maybe you're stronger at synthetic. You can always check. Okay, it's always going to be true. That's something called technically the factor theorem. Long story short, remainder of synthetic should be the same thing as is always if you've done it correctly. Same thing as the function value and vice versa. But what we haven't gotten to talk about is how do we use this idea to help us. Can I come back to the nasty one for a second? What if the directions of this did not say divide? What if the directions of this said instead, oh my goodness, there you go. Struggle. Find all the factors of that guy. That means it wants parentheses, 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 find the factors to find the zeros. Why is it harder than the ones that we saw in section 2.2? There's an x cubed, and we can't pull out an x, right? Well, that's not fun. Can we use all our quadratic tricks with an x and all that jazz and grouping? No. Can we use this guy to help us factor? He didn't even go in. So what if they said to factor, this guy doesn't work. Could we try somebody else? X minus 1, x minus 2, x plus 3. Can we do synthetic after synthetic after synthetic on this huge witch hunt for which one gets a remainder of 0? I guess so. But what's the shortcut, maybe, for doing lots of different synthetic divisions?
Plus the remainder.
Yeah, C, because the remainder, in order for us to find a factor, remainder has to be what? 0. So couldn't we try plugging in? Well, 0 is not going to work. Could we try plugging in 1? 1 would be the 0 in the box. Let's just plug in, and then if we can find a 0, we'll finally figure out one that works. So if we plug in 1, that's 6 plus 7 is 13. No, that doesn't work. That's not 0. What if we plug in 2? 8 and 48. And then we have 28. 48 plus 28, that's going to be a lot bigger than, no. How about negative 2? Negative 2 will be negative 48. Negative 48 plus 28. That'd be negative 20. Oh, no, that doesn't work. Struggle. This one's going to be a hard one, right? We tried plugging in 3 and 4 and 5 and 6. Okay, there has to be something to help, and there is. There is something to help, and we'll actually talk about it a little bit more in section 2. I don't know, what section is that? 2.5? But for right now, the book's just introducing us to this idea that if we can find one where the synthetic is a remainder of 0, or where the plugging in is a remainder of 0, we can simplify our lives. And here's an example to that end. They're not making you totally do it on your own until section 2.5. But they are introducing you to the idea that in order to factor something like this, we can't pull out what makes it a cube. We're stuck with this cube. How do we factor? They start giving us a hint, like, hey, why don't you try 2? Okay, why don't we try 2? All right, fine. They say, why don't you try 2? And we just said, well, maybe plugging in might be faster than synthetic. We're going to use synthetic. Don't worry, the directions say to use it. But this problem says, use synthetic to show that x equals a is a solution. I just introduced you guys to the idea that maybe they won't even give you something to try and you have to try your own. You don't have to do synthetic after synthetic after synthetic and keep on finding ones that don't work. If you could have just plugged in and checked before the synthetic. So remember, the remainder, what we're going to get, is going to equal what happens when we plug in. And when we plug in, guys, what do we get? Has anybody checked it yet? Exactly. So what if we didn't know 2? We tried plugging in 1, that's not 0. Tried plugging in 2, hey, it's 0. Because we have 8 minus 14 plus 6. 14 minus 14 is 0. What does this tell me? He goes in evenly. Which means x minus 2 is a factor. If you guys read your directions, we're not done yet because they want us to find all of the factors. How do we do that? Once we find one that works, like this 0 of 2, which comes from the factor of x minus 2, we're going to do synthetic and break this guy down. Because we can say, I know you're a cube, but I figured out one of your linear pairs. If I can take him away, you'll just be a quadratic, and I can deal with that. So, let's deal our coefficients. Our coefficients would be 1, 0. Good. 1, 0, negative 7, 6. Who am I putting in the box? Positive 2. Good. Who's coming down?
1.
What side pattern? Multiply and add. So multiply 2 times 1, bring it up. 0 plus 2 is?
2.
Multiply.
4.
Multiply.
6.
Did it go in evenly? The answer is yes. What can I say? Well, be careful. I can say that f of x divided by x minus 2 is this answer. But I'm trying to factor, so a better way of stating it wouldn't be the division, which I'll show you that. I could say the division, because that's technically all we did so far. When we put that 2 in the box, we were dividing by his factor, x minus 2. And as, Kelly, I think you were saying it, right? The 1 and the 2 and the 3, they do symbolize an x squared term, an x term, and a constant. But that's the answer to a division problem, which is good and all, but they didn't ask us to answer a division problem. They asked us instead to find find the factors. So it's better for us to move this x minus 2 to the other side and say, hey, I know how many times x minus 2 goes in, and it goes in evenly. Which is good. But we're not done until we break him down as well. But question, who's easier to break down? This cubic guy at the very, very beginning or this quadratic? Yeah. So once we took out the x minus 2, now we have something that we can factor in an old-fashioned way. How do we factor this guy? Not the x minus 2. He's good. He's solid. He's established. But how do we factor that guy?
X minus 1, x minus
You can do that. Factors of negative 3 that add to be 2. 3 and 1? Who's negative?
Negative 1.
Good. So I need to multiply to get a negative 3, add to be a positive 2. Now, some of you are like, I know exactly how to finish this problem, and that's great and all. But not all quadratics have a nice pretty 1 in front. So just to remind us really quickly, technically what this does, that 3 and that negative 1 tell us how to split up. How to split up our quadratic. Just a reminder. With grouping, you can go ahead and take out who's in common. I see a negative 1 in common. Just a reminder. Then we can go ahead and get to our x minus 1, x plus 3, and all of that is with the original factor of x minus 2. Now, could some of you have jumped from this x to those factors right away? Yeah. You could have seen the positive 3 and the negative 1 and jumped to x plus 3 and x minus 1, but remember, that only works when the leading coefficient is. Otherwise, you have to do the splitting up and the grouping. Go fast. You could have used the quadratic formula, which you would have found is a positive 1 and a negative 3, so you would have had to take those zeros and make the factors out of them. Does that make sense? So you could have taken A, B, and C, but when you would have done that, you would have ended in a positive 1 and a negative 3, just the numbers, so you would have had to make your factors. So x minus the positive 1 and x minus the negative 3 would have gotten you the answers of that. Kiddos, remember, this section is just introducing you to the idea that synthetic division and even the idea of plugging in to figure out remainders can help us figure out from this huge long list of possible factors or possible zeros, which ones work. And the only ones that work are the ones that, when plugged in, equals 0. When synthetic division is done, the remainder is 0. And once you find one that works, you can break down the polynomial. What if you had like a 5th degree polynomial? Can you imagine that for a second? If you had an x to the 5th with all this yucky factor. How many zeros would you have to find and do synthetic division to the polynomial in order to get it to be a square? If you had a 5th degree. Every time you do a synthetic division, it goes down by 1, right? So if you found one factor, you can make it a 4th degree, not good enough. If you found 2 factors, now it's a 3rd degree, better. You would have to find 3 factors and do 3 synthetic divisions before you would get to a quadratic you could finish off. So the higher the degree of the polynomial, the harder it gets. But remember, this section is going to help you out by giving you one that works. In section 2.5, it says, okay, training wheels off, we're just going to give you a polynomial, let's go for it. But we'll work up to that. We'll work up to that. All right, cool kids. I'm going to have you guys get out your spirals. I need to pass back your chapter 1 tests. They've been graded for a couple days. TAs were recording. I was finishing this weekend, etc. You guys are going to write down this homework if you have not yet. If you look at the screen, doesn't section 2.3, doesn't it look kind of shorter? I'll finish you. No? 2.3. What are you guys looking at? This is the same as those? Okay. Anyway, this assignment looks shorter. Except Maybe some of the end ones take a little bit of work like the synthetic that we did. I don't think it's going to be too bad. Remember, this is introductory to this section. 2.5 is a bit of a beast. So we're building skills here. We need to talk about imaginary numbers for a little bit here. This will be a mostly nice homework. Just reviewing like I. But we're going to go ahead and build the framework, build the foundation for 2.5, which is a bit of a beast. So please take your time on this homework tonight. Write this assignment down if you don't have it yet. In just a second, I am going to pull up the book so you can see the beginning of homework. What's the first problem that you guys have? Oh, it's not 2.5. Sorry, you're 2.3, aren't you? I had the wrong section up. Some of you already started homework. Perfect. If you need to borrow a book or if you have a book, just go to where you left off. But the rest of you guys, I'm showing a lot of problems up here. And you can get a really good start in homework done while I pass back your tests and correction papers. We'll talk more about the tests and corrections tomorrow if we run out of time. Okay, you already started homework? Cool beans. Pick up where you left off. If not, ready, set? Keep going, guys. Take one, pass back. Kiddos, we're being productive. Don't waste time. Time is precious. We all